When you think of the North Pole, you're probably picturing a fixed, static spot right at the very top of the globe, right? But what if I told you the real North Pole, the one your compass actually points to, is on the move? Yeah, it's on the run, and we're going to dive into why.
All right, so first things first, it turns out there are actually two North Poles. Over on the left, you've got the geographic North Pole. Just think of it as the top of the Earth's spinning axis. It's fixed, it's reliable, it doesn't go anywhere. But then there's the magnetic North Pole on the right. That's the one compasses are drawn to. And this one, it's anything but fixed. It is a constantly shifting target, and lately, its movement has been, well, pretty dramatic.
How dramatic are we talking? Right now, it is racing across the Arctic at an astounding 50 kilometers per year. I mean, to put that into perspective, before the 1990s, it was just kind of crawling along at a leisurely 10 kilometers a year. This sudden, massive acceleration is exactly what has scientists so captivated.
So, to really get a handle on this, let's trace this pole's incredible journey and take a look at the history of its wild wanderings.
Okay, so we've been tracking this thing's movement ever since it was first pinpointed way back in 1831. And for more than 150 years, it was this slow, predictable crawl. But then, sometime in the 1990s, it's like it just slammed on the accelerator. And today, it's not just moving fast, it's on a very clear path, racing away from its longtime home in the Canadian Arctic and making a beeline for Siberia. So what on Earth, or maybe more accurately in Earth, is causing this? Well, to figure that out, we've got to look deep inside our planet, at the molten engine that's driving this whole phenomenon.
The answer lies thousands of kilometers beneath our feet in a process called the geodynamo. See, deep in the Earth's core, there's this massive ocean of molten iron and nickel that is just constantly churning and sloshing around. All that movement of liquid metal basically acts like a giant electrical generator, creating the magnetic field that surrounds and protects our entire planet.
The best way to think about what's happening is like a magnetic tug-of-war deep, deep underground. For a very long time, a big patch of strong magnetic flux under Canada was the anchor, holding the North Pole pretty steady. But now, that Canadian patch is getting weaker. At the same time, a rival patch under Siberia is getting stronger and stronger. So Siberia is winning the tug-of-war, and it's literally pulling the magnetic pole over to its side. This brings up a really good question. How in the world do we know all of this with such incredible precision? Well, let's take a look at our eyes in orbit, the amazing satellite constellations that are tracking every single wobble of this magnetic field.
We have this incredible team of sentinels up in space monitoring all of this. The star player is definitely the European Space Agency's SWARM mission. That's a trio of satellites built specifically for this job. But it's a real team effort. Other missions like Cryosat-2 and the GRACE satellites, they all pitch in with vital data. And all of them are building on the groundbreaking work done by pioneers like Champ and Ørsted.
And this is where the strategy scientists are using gets really clever. On one hand, you have the gold standard missions like SWARM, which are hyper-accurate. And on the other hand, you have what are called platform magnetometers on satellites like Cryosat-2. Now, these are basically just the compasses the satellites themselves use to navigate. They aren't as precise as SWARM's dedicated instruments, but they help fill in all these crucial data gaps, giving us way better global coverage. So by combining the data from both types of missions, scientists can build a much richer and more complete picture of what our planet's magnetic field is up to, almost in real time. It's a really fantastic example of scientific ingenuity. Okay, so we've got all this precise data streaming down from space. Now we can finally ask the biggest question of all, why does any of this actually matter to us? In this last section, let's connect the dots from this deep Earth science to our daily lives, from GPS glitches all the way to massive planetary scale shifts. So yeah, why does a wandering pole matter? Well, it matters a lot. Everything from the compass app on your phone, to military navigation, to the systems that guide airplanes, relies on an accurate map of the magnetic field called the World Magnetic Model. As the pole moves, that model has to be updated more and more often to stay accurate. And even more fundamentally, this magnetic field is our planet's shield. It protects us from nasty solar wind. A changing field raises some big questions about the strength of that shield.
Now, the most extreme version of this kind of change is called a geomagnetic reversal. That's a complete flip-flop of the magnetic north and south poles. These are actually a normal part of our planet's history, even if they happen erratically. But the last full one was about 780,000 years ago. And because it's been so long, the question of whether we're due for another one is a pretty hot topic in science.
Now, it's really important to separate a full reversal from smaller wiggles. A recent and pretty provocative study by Belly Goshu suggests there's a pattern of these smaller fluctuations, which the study calls reversal events, that happen with surprising regularity, about every 50 years. And based on that pattern, the study even forecasts another one for 2025. And they get even more specific. The study's model predicts a very precise location for the magnetic North Pole in 2025, placing it super close to the geographic pole, but deep on the Siberian side of the Arctic. It's a really fascinating prediction, but it is just one interpretation of the data.
However, and this is the really crucial takeaway, it is so important to remember what the broader scientific consensus is. While models like the one we just saw are interesting thought experiments, most geophysicists agree the long-term movement is fundamentally unpredictable. That churning liquid metal in the core is a chaotic system, and that makes precise, long-range predictions like that basically impossible right now.
So we're left with this fascinating reality. We can sit here and watch our planet's magnetic shield shifting in real time with incredible precision, but we can't really be sure where it's all headed in the long run. It's just a powerful reminder of the dynamic, ever-changing, and kind of wild planet we live on. And it leaves us with a pretty big question. Are we prepared for what comes next?